Today we will consider a new topic called goal programming. Here we look at multiple objectives or goals. So far in all our study in linear programming and related topics, we have looked at OR problems which have a single objective which either minimizes or maximizes a linear function. Now, do we or can we have situations where there could be multiple objectives? If so, what do we do? Do we solve as many linear programming problems as the number of objectives, or what do we do there? And first of all, how do we model such a situation? Now, these things are handled in what is called multiple objective programming, and goal programming is one such method to handle multiple objectives. There are other methods, but goal programming is the most commonly used approach to address situations which have multiple objectives. As usual, we will take a small example and then try to illustrate how these multiple objectives or goals are met. So, let us look at a problem. Say for example, you make two products A and B, and say they are made out of three chemicals 1, 2 and 3. A requires 3 of 1 and 5 of 2, B requires 1 of 3, B requires 4 of 1 and 6 of 2. Profits are 70 and 80 respectively. Availabilities are 50 and 60 respectively. Two additional sentences are given which are like profit is to be kept above 800. Item C or item 3 to be ordered, or quantity of item ordered is 8 or less. Normally, if we were to model this as a linear programming problem, what we will try to do is we would first define the decision variables, say x1 and x2 be the quantities of A and B produced. It is a very standard problem that you can directly formulate. So, you will have something like 3x1 plus 4x2 is less than or equal to 50, 5x1 plus 6x2 is less than or equal to 60, x1 less than or equal to 8 because you do not want to order more than 8, and then you will have an objective function. You will not use this 800, you would simply say maximize 70x1 plus 80x2 and solve the problem, and then if you come up with an optimal solution whose objective function value is more than 800, you say that the 800 target can be achieved. Otherwise, you would say the 800 target cannot be achieved and only this much can be achieved. That is what we would do normally in a linear programming formulation of this problem. Now, in a goal programming formulation, what we do is we kind of take these sentences as they appear in the first place, and then there is another sentence which would say the effort is to minimize total production so that transportation is easy. So, you can assume that another sentence is also given which says minimize total production such that transportation is easy. Now, this adds to the conflict because if you leave out this sentence, you have a clear single objective which would be to maximize 70x1 plus 80x2. Now, if you want to do this, if you want to include this also, what you can do conveniently is change the objective function to minimize x1 plus x2 and try to put this as a constraint which is like 70 x1 plus 80 x2 to be greater than or equal to 800. So, that way you use all the numbers that are given to you. Now, when we want to do this as a goal programming problem, we need to do this. 1, identify what are called rigid constraints. And then look at all these. For example, the availability of this 50 and 60 are very rigid as a constraint, whereas if you had written a constraint which is like 70 x1 plus 80 x2 greater than or equal to 800, okay, this will not qualify to be a very rigid constraint because of the way, I mean it depends again on how you interpret it. For example, if this sentence is written as it is desirable to maintain a profit, say it is desirable to have profit greater than or equal to 800, okay. It is desirable to order a maximum of 8 for item 3. Suppose we start using sentences like this which happen in practice. When you produce, these are the only rigid things. For example, these have to be bought from vendors or suppliers. So, you know that these vendors cannot give, or in the present system you cannot have more than 50 or 60 per day. So, they become rigid constraints, whereas something like profit to be kept above 800 or quantity of item 3 to be ordered being 8 or less. So, these things become what are called goals. They are not rigid constraints, but they become goals. So, you have to categorize them as what are rigid constraints and what are targets or goals. This 800 is like a target or a goal that you want to achieve. You want your profit to be as much as possible, but you want it to be around 800, but you do not want to put a rigid constraint saying I want a profit of 800 or more. If you start putting those rigid constraints, you may get into an infeasible situation. You do not want to get into that kind of a situation because you still want to produce something and make some money. So, the rigid constraints have to be separated, the goals have to be separated. Now, as far as this problem is concerned, there are two rigid constraints, these two are your rigid constraints. For example, we define the same x1 and x2 as the quantities of A and B produced. So, your rigid constraints will become 3x1 plus 4x2 less than or equal to 50 and 5x1 plus 6x2 less than or equal to 60. So, this is your rigid constraint. Now, the rest of them are taken as they appear, unless otherwise stated they are taken as they appear. These targets or goals are now assumed to have different weightages, and these weightages depend on the order in which they appear unless otherwise stated. So, the rest of the three things, for example, the first one that I want to satisfy is this 800, the second thing I want to satisfy is this 8 or less, and the third thing I want to satisfy is to minimize the total quantities to be produced unless otherwise stated. So, I take them in this order. Okay. Now, these are written as 2, 3 and 4 respectively. All the rigid constraints are bunched together, the rest of the targets are taken as they appear, and it is also assumed unless otherwise stated that it is most important for me among the three to do this, consider this first, and after I have set or achieved this target, I will try to achieve this target, and then I will try to achieve this target. Right now, we have not given a target for this, we will come to that as we proceed. Now, these two have targets. So, the third one is 70x1 plus 80x2. Moment I put it as greater than or equal to 800, it becomes a rigid constraint, and then there is an 800 here. And then as far as the third part is concerned, this one is item 3, so x1 and there is an 8 associated here, and here there is an x1 plus x2 which is to be minimized, we do not know the target. Now, in all goal programming formulations, you will have only equations and you will not have inequalities. So, the rigid constraints will now be written as 3x1 plus 4x2 plus eta 1 minus rho 1 equal to 50. Yeah.
Sir, why can we not solve this as a straightforward LP?
No, the reason why you do not want to solve a straightforward LP is you could get into infeasibility. Now, if you look at very practical problems, if you are trying to formulate a practical situation into a optimization problem, what you will know among the data are the resources, and what you will not know are the costs and the profits. So, an organization would say clearly that this 50 and 60 I know very well, I want to make a profit of 800, but I am not going to put it as a rigid constraint. At the same time, it is not my objective either. I have different things that I want to do. I am worried about a profit of 800, I am worried about this resource because I have a weak supplier who is not able to give me what I want. This guy says he can give me only 8 or less, and I am also worried about this because I want to minimize the transportation. I may not have trucks to dispatch things. So, it is not that I have a single objective. I have multiple things which are there with me, which make the modeling as well as the real life problem little more difficult.
So, but what do we mean by this is not a rigid constraint? If the profit is 750, then it's okay.
Yes, I would prefer an 800 plus, but if it is 750, I will accept it. I want your problem to tell me what exactly is the maximum achievable. Similarly, this 8, yeah.
Are we saying weights to those requirements? Are we saying that this is the most important thing?
There are several ways of solving. We still have not come to that. One you can do is just keep only the rigid constraints, take all the targets into the objective function. So, if you have 3 objectives, you could put a W1 O1 plus W2 O2 plus W3 O3, where O1 O2 O3 are the objectives. You can do that. That is called a weighted approach, and that will reduce to a single linear programming problem. It will finally reduce to a single objective problem. Now, this is called lexicographic minimization. That is, you take these as they appear and first satisfy the first, and having satisfied the first, go back and satisfy the second, having satisfied 1 and 2, look at 3, and so on. There are different ways of doing it. I am going to touch upon only the second way, that is the lexicographic way.
Will we say you got 850 but then not able to satisfy the 8? Will we say go down to say 700 or something and then satisfy 8?
Okay, in a typically lexicographic approach, if you have taken the first objective and if you are not able to satisfy even the first, you will not look at these second, and so on. We will see as we solve these problems. We are just now trying to formulate them. So, we will take the same, I am going to do 2 formulations and 2 solutions. You will see all those aspects as we solve. Yeah, right. So, we write this in the form of an equation. Because it is a rigid constraint, you know that the rho does not make any sense, because it is a rigid constraint. It is like your eta 1 takes on the role of a slack variable. The rho 1 basically takes on the role of a negative slack, and since it is a rigid constraint, the rho 1 does not make any sense to you. However, for reasons of consistency, every constraint or equation that you write will have a corresponding eta and rho, even if the rho is irrelevant. But you will see that the rho is relevant in a different way. So, this becomes 5x1 plus 6x2 plus eta 2 minus rho 2 equal to 60. Now, these are the only 2 rigid constraints that you have, and if you want an x1 x2 which is a solution to this problem, that x1 x2 must satisfy all the rigid constraints. It has to satisfy all the rigid constraints, correct, which means that I should not have rho 1 and rho 2 in the basis of a simplex table. Where the moment I have a rho 1 and a rho 2, it implies that this left hand, this 3x1 plus 4x2 is greater than the right hand side, only then I have this rho coming in. Remember, I have an eta minus rho, which is like an unrestricted variable modeling. Only eta or rho will remain in the basis, both will not remain in the basis. So, if I have a rho positive, it implies that the rigid constraint is violated. So, any x1 x2 that has rho 1 plus rho 2 equal to 0, because rho 1 rho 2 are greater than or equal to 0. If I have an x1 x2 such that rho 1 plus rho 2 is equal to 0, then it is feasible to the rigid constraint. So, what I want to do is, I want to minimize here, I want to minimize rho 1 plus rho 2. If I get a 0 there, it means any x that gives me rho 1 plus rho 2 equal to 0 is feasible to the rigid constraint.
These are artificial variables. These are like artificial variables.
These are like artificial variables, yes, in a sense artificial variables, because when you solve them finally, you are only going to do this minimize rho 1 plus rho 2, which means they will have a coefficient of 1, which is like a two-phase method of linear programming, which we did not cover in detail. For example, if you take a linear programming problem that has artificial variables, this is for the general class, we looked at the big M method to solve such problems. We gave a big M into the objective function, and so that it does not appear in the optimum basis. There is something called a two-phase method, where you give a plus 1 to the artificial variables, give a 0 to all other variables, decision and slack, and then minimize. For example, if you have two artificial variables, you will just have minimize a1 plus a2 subject to the whole thing. Now, because if there is a basic feasible solution to the original problem, the artificial variables should not lie in the basis. So, they will go out of the basis and you will get z equal to 0, and then leave out the artificial variables and start from this basic feasible solution and proceed. That is called a two-phase method, which many books will cover, which we did not do in detail in the earlier course. What we will do while solving is something very similar. We will give a plus 1 to these etas and rows always, unless there is a different weightage, but etas and rows will always have a plus 1. Now, this is my third thing. So, this is 70x1 plus 80x2 plus eta 3 minus rho 3 is equal to 800, and remember, I would like to have a profit of 800 or more. What does that mean? What does that mean? It means I want to minimize the eta, because the moment I have an eta coming in, it means I am going to have a profit which is less than 800. Remember, again, between these two, only one of them is going to be in the basis. So, if this eta is in the basis with a positive value, it means that I am having a profit of less than 800. So, in order for me to have a profit of 800 or more, which is desirable, I would like to minimize eta and keep eta at 0. It also tells me something. If I am not able to get eta 3 equal to 0, I get eta 3 equal to a positive value, it means I cannot get this 800. So, here the objective is to minimize eta 3. There is a simple way to look at it. See, any less than or equal to constraint will push rho into the objective function, any greater than or equal to type constraint will push eta into the objective function. Even though this interpretation is not very technically correct, it is a very nice thumb rule to understand. You want to keep something more than 800 or above, which means it is like having a greater than or equal to constraint. This will automatically push eta into the objective function. As far as the fourth one is concerned, it is less than or equal to. So, x1 plus eta 4 minus rho 4 is equal to 8, and I want to minimize rho 4. Now, the last one is x1 plus x2 plus eta 5 minus rho 5 is equal to what? There is no target that is given in this problem. So, you can actually assume a target. So, let us assume a target of 8. This is assumed. Okay. Of course, at this point you may be tempted to say that depending on what target I assume, my solution may change, because it is like explicitly changing a right hand side in a linear programming problem. Actually speaking, it would not, because it is the last of the condition that you are trying to model. When we solve it, you will see this. So, right now I am going to ask you to just assume that some number here, you can put 0, you can put 100, you can put anything. In fact, the easiest thing to do is to put a 0. It just to put a 0 and proceed. I mean, it might give you infeasible, but still does not, it is all right. You can just put a 0 and proceed. When we solve it, you will see why the whole thing is. I mean, we will try to solve it today or in the next class. Right. So, what will be the objective? Now, the objective, this is like minimizing, this is minimizing rho 5. Because it is like saying I want my x1 plus x2 to be less than or equal to 8. Okay, this is like minimizing my rho 5. So, So, what you will do, all these will remain as they are. Now, your objective function will look like this: minimize. I am going to take all this into the objective function. So, I will just say rho 1 plus rho 2 comma eta 3 comma rho 4 comma rho 5. So, I will take this out. Subject to x eta rho greater than or equal to 0. So, this is your goal programming formulation for the first problem. We will see later how we solve it. We will try to solve it, this particular example we will solve it using the graphical method. We will do another formulation which we will try to solve using simplex, so that you get a feel of how to solve it using graphical and how to solve it. I mean, one can go on explaining goal programming for hours, but in this course we will not spend more than 2 or 3 classes on how to do this goal programming thing. Right. So, this is the formulation as far as the thing. So, what have we learned? One, all goal programming formulations will have equations. They will all have every constraint is written as an equation ultimately with an eta and a rho. Depending on the nature of the constraint, whether you want to minimize something or maximize something, or whether you want to keep something below a certain level or above a certain level, you will push the corresponding eta or rho into the objective function. All rigid constraints are bunched together, right? They are bunched together and then their corresponding things are written here. For example, if you had a greater than or equal to rigid constraint, a third rigid constraint, then it would have become rho 1 plus rho 2 plus alpha j, some alpha k or whatever, I am sorry, eta k. So, it can be a mixture of etas and rhos, that is also allowed. It is not that it should have only this. You will have as many terms here as the number of rigid constraints, and depending on the nature of the rigid constraint, you will have this written. No, the only thing is when there is actually nothing wrong in doing it. One of the reasons you bunch them together is you want equal importance to all of them. Moment you say rho 1 comma rho 2, it means you are giving more importance to this constraint than this constraint. So, you do not normally do that. So, right. So, this is the first example. We will take another example and try to understand a couple of things and then proceed to solving this problem. Right. Always the objective is a minimization. You will not have maximization problems here. All these will be greater than or equal to 0. Etas and rho, sometimes books will give d plus plus d minus. So, it is like dj, which is called a positive deviation and a negative deviation from the target or the goal. We use eta and rho. It is just a matter of terminology. Could use anything. Now, let us look at a second example. Let us say there are two products A and B are assembled. A requires 4 hours in assembly and B requires 3 hours of assembly. Regular time available in assembly is 90 hours. Profits are 7 and 8. Say overtime is available, but reduces the profit by 1. Demand are 30 and 40 respectively. Goals are 1. targets have to be met and regular time is 90, minimize overtime, maximize profit. So, let us start the formulation as we try to formulate a linear programming problem and then proceed. Let x1 and x2 be the quantities of A produced in regular time and overtime. Let y1 and y2 be the quantities of B produced in regular time and overtime. So, there are three things in the rigid constraints, which are basically two things in the rigid constraint. Target has to be met and the regular time availability is 90. So, you will, what is it, the target has to be met is given by this, x1 plus x2 should be, or plus eta 1 minus rho 1 is equal to 30, and y1 plus y2 plus eta 2 minus rho 2 equal to 40, and x1 plus y1 plus eta 3 minus rho 3 equal to 90. 90 is the regular time availability, and these are your rigid constraints. Okay. Regular time 90 is a rigid constraint. What is, see, when you are given this information in this form, whatever is given first in a bunch is a rigid constraint. That is also an assumption unless otherwise stated. See, one of the difficult things in goal programming is to first understand and interpret it suitably. So, I am trying to tell you what you should do unless otherwise something is stated. So, this 90 is not a goal. I mean, you should also look at it very practically. Every organization will be able to define its regular time capacity very accurately and nicely. They will tell you that maybe at this much overtime is, for example, if an organization runs 5 days a week and 2 shifts a day, you know, 8 into 2, 16 hours per day into 5 days a week, 80 hours is what you have as regular time capacity. The overtime is a very tricky thing. You may work on the 6th day and get another 16 hours. You may work 3rd shift and get some more hours. So, they will only say these are the possible things that are available. So, you can say that the regular time thing is a rigid constraint. Now, both these are your targets or goals without the actual target being specified. For example, both are kept free as open objectives. It does not say, for example, keep overtime restricted to 50 hours. It does not say keep my profit close to 400 or whatever, right. So, first let us do this. Okay, the regular time is 4x1 plus 3y1 plus eta 3 minus rho 3 is equal to 90. Yeah.
We already given that overtime reduces the profit by 1.
Yes.
We choose minimize overtime to be having more priority than maximizing your profit in the goals itself.
Okay, it depends again. Right now we will not question this. Questioning this is something else. It's one level above. See, you should look at this whole thing not from solving an optimization problem or an OR problem, but you should try and understand the issues that are there in modeling real life situations or complex situations. That is it. At this point, I would not ask you to worry about why this is a higher priority thing than this. I would possibly ask you to take it as it is. But if you want to question it, that questioning will come later after you solve it and say this is a solution, and then if I change this, what happens? If it's beneficial, then I do that. Right. So, this would mean this is like minimize rho 1 plus rho 2 plus rho 3. That is what you have, rho 1 plus rho 2 plus rho 3. Yeah, target has to be met. So, you will have eta 3. No, sorry, one second. Eta 1 plus eta 2 plus rho 3, because you want to meet the demand. So, you will have eta 1 plus eta 2 plus rho 3 coming in. Now, these two things we do not know. So, this will have a left hand side of x2 4x2 plus 3y2, and we will right now keep the target as $20. So, plus eta 4 minus rho 4 equal to 20, we will just keep this, and the other one would be 7x1 plus 6x2 plus 8y1 plus 7y2 plus eta 5 minus rho 5 will be equal to, keep it at 200 as the profit. Okay. Okay, something like 200. Both these are now defined by us, they are not defined in the problem. Now this will become, I want to minimize the overtime, so I will keep overtime less than something. So minimize rho 4, this will be minimize eta 5. So I will have minimize eta 1 plus eta 2 plus rho 3, rho 4 and eta 5. Now before we, this is the second formulation. Is there any questions? Again x, eta and rho greater than or equal to 0. Any questions or? Right. Now we have made two important assumptions here. We have made 20 here, we have put the 200 here. So we are not sure whether these are right or these are poor estimates or these are good estimates, we do not know. The only guideline that we may have in the absence of these numbers not being given to us is something like this. For example, I have a demand of 30 and 40 of these. So I may need, for example, so many hours, 30 into 4 is 120 plus 240 hours is what I may need, right. 40 into 3 hours, 30 into 4 hours. So 240 hours is what I need. I have 90 hours of regular time. So if I want to meet all these things, I may need another 150 hours. So maybe my estimate on this is poor, correct? Is that okay? My estimate on this is poor. So I may put a reasonably higher estimate and work. Now what is the risk in doing this, which is a question that was asked earlier. Now the one thing that I want is, when I solve this, what I am going to do, I am going to take the first objective and I am going to solve with all these constraints. I will get an answer. Now what I will do is, I will retain that answer and then try to solve the second. So whatever I have as a solution to the second should not deviate from the first, which was what was asked. For example, if I think that the minimum over time that is needed is some 100 hours or whatever, when I solve this, now when I solve the third, I should not end up creating more overtime for the sake of more profit. Or you will also realize, now how does this contribute? Now all the rigid constraints are modeled first, and any x, y in this case that satisfies all the rigid constraints will and should have an objective function value of 0. If either eta 1 or eta 2 or rho 3 is positive, which means the sum is positive, it means that the corresponding rigid constraint is being violated. So they are also very loosely defined. It is not that there is only one point which satisfies eta 1 plus eta 2 plus rho 3 equal to, there are plenty of points. If you look at it very carefully, moment we draw the graph, you will realize. So the first part of this formulation should always have an objective function of 0. If you have an objective function value of 0, it means you have these rigid constraints have a feasible solution set. then you will move to the next one. Now I will minimize this row 4 subject to the condition that this is satisfied, which means subject to me being inside the feasible region, I am trying to satisfy this. Suppose I put a poor target like 20 here, and if it turns out that in order to meet the rigid constraint, which is to meet this 30 and 40, I may need say 140 hours extra, which means this will become 120 if I have put a 20 here. If I put 100 here, this would become 40. So, but if I put a 200 here, then this will become a 0. It will not become minus 60, it will still become a 0. So, if I put something sufficiently large here, then it means I am playing very, very safe. But then I am also making a mistake of a different kind, because my organization may not like to start with a very large acceptable value. Now, why are we discussing this so much? Now, the moment I put a smaller value here like 20 and I realize that I get a positive value here, it means that my target is to be revised and I may not be able to achieve this 20, and that solution which actually minimizes, which suppose my total needed is 140, I have put a 150 or whatever, 140 say, I have put a 20 here, which means I will get a 120 here. The moment I get a positive value here, I will not proceed further. I will stop the algorithm and I will evaluate the eta 5 for the solution that I already have. Now, that is the advantage or disadvantage of this lexicographic approach. Moment I am unable to proceed, and the fact that I am unable to proceed will be indicated by a positive value coming here in any one of these. The moment I get that positive value, I will not optimize further, but I will evaluate the rest of the objectives further. So, it becomes very important to define this. The last one is fine, the last one is all right. For example, if the organization has agreed for a 200 overtime, say the organization is okay, I go back, discuss with them what is the realistic overtime you want, and they say 200, whereas I need a 140. So, rho will not be negative, but rho will be 0, eta will take a value. Now, I can go further and optimize this. So, if this being the last one, whether I put 200 or 2000, it does not matter, because if this estimate is very high, then this is also going to be 0. If this estimate is poor, this is going to give me a positive value and I will stop. So, when it is the last of the targets that for which you do not have the value, you can have any arbitrary value and proceed. But the moment you do not have a value assigned to more than 1, then what you assign to the last but 1 is going to decide whether you can optimize further or not. So, you need to be careful about that. That is what this example explains to you. There can be situations where this may be tight, this may be loose, but the order in which it has come would ensure that the tight one would give a positive and I do not optimize further. Whereas, if I had interchanged this, the looser constraint would have come first and then it would not have affected. So, the order in which they appear are also important in all these kinds of problems. Okay, now, with this we will go back to the first one and we will try to solve the first one, and then we will try to solve the second one. The first one we will solve by the graphical method, the second one we will solve by the simplex method, so that you understand how both these methods are used to solve goal programming problems. Now, we go to problem 1 again. Minimize row 1 plus row 2, eta 3, row 4, row 5, subject to 3x1 plus 4x2 plus eta 1 plus rho 1 equal to 50, 5x1 plus 6x2 plus eta 2 minus rho 2 equal to 60, 70 x 1 plus 80 x 2 plus eta 3 minus rho 3 is equal to 800. Minus rho 1, x 1 plus eta 4 minus rho 4 equal to 8, x 1 plus x 2 plus eta 5 minus rho 5 is also equal to 8. Now, you can leave out these etas and rhos because they are like slack variables. So, you go back to your early linear programming, so you will always leave out the slack variables, right. With the slack variable, a 2 variable problem will become 4 variables, but this is still a 2 variable problem in spite of the additional 5 etas and the additional 5 rhos. So, it is a 2 variable problem, you can solve it by the graphical method. So, let us go back and draw the graph for this. So, you will have x 1 and x 2 here, 3 x 1 plus 4 x 2 equal to 50. So, let us put some numbers, say 5, 10, 15, 20, 25, 30, 5, 10, 15, 20, 25. So, 3 x 1 plus 4 x 2 equal to 50 will give me x 1 equal to say 6, implies x 2 equal to 5. So, I have one point which is like this. This would give me, no sorry, this would not give x 1 equal to 10, x 2 equal to 5, come here 30 plus 20. So, this would give x 1 equal to, I put this for example x 2 equal to 10 would give x 1 equal to some 3 point something. So, I will have something like this 0 comma 12.5. So, this will be my now this is 12 comma 0 and 0 comma 10. So, this 12 comma 0 and 0 comma 10, right. This is what I have. First one is 16 point something. So, both are less than or equal to type. Now, what happens? This is the first constraint. This is the first constraint. So, if I put this as say 60, then this will come here parallel to itself and it will move above. So, 60 would imply eta 1 is equal to 10. So, this is the direction of increase of eta and this is the direction of increase of rho, or the other way, sorry, this is the direction of increase of rho, this is the direction of increase of eta. I will explain it again. So, if I put this equal to 60, if I put 3 x 1 plus 4 x 2 is equal to 60, right, then it means that when if I shift this is a point here would mean that 3 x 1 plus 4 x 2 is greater than 50 and therefore, this has a positive rho. A point inside will have 3 x 1 plus 4 x 2 less than 50 and will have rho equal to 0 at a positive eta. So, if I want to minimize rho, then this is the less than or equal to thing, this is rho equal to 0 and any point under this will have rho equal to 0. Now, similarly, this any point here will have rho 2 equal to 0. It turns out that this constraint dominates the other. So, any point inside this now has any point inside this has rho 1 plus rho 2 equal to 0. So, your first rigid constraint is actually represented by this particular triangle. So, now you write this one 70 x 1 plus 80 x 2 is equal to 800 Now this is given by the point 0 comma 10 which is here, and the other one is 8 by 7 is roughly how much, 1.2, 1.4. So just 80 by 7, 11.4, 11.4, say somewhere here, so is less than this. So this is my point. So this is the other one. This is the, now I want to, so this is increasing rho, this is eta equal to 0. So my feasible region reduces to something like this. This is my feasible region here. So any point inside this region now satisfies this is equal to 0 as well as this is equal to 0. Now I have another one, x1 less than or equal to 8, which is somewhere here. So this will be my x1 less than or equal to 8. This is my x1 less than or equal to 8. This is the direction of increasing rho. So this is rho equal to 0 or rho 4 equal to 0. So now your feasible region reduces to this alone. I am just shading off the entire thing. So your feasible region reduces to this. This is not included. So this part alone is your feasible region. You still have a feasible region. So any point inside this region will give you all this equal to 0, including rho 4 equal to 0. So every point inside this region is capable of satisfying whatever conditions that you have. You can choose any point that way. And the last one is x1 plus x2 is less than or equal to 8. So I have to go back here. Now, yeah, this is my, yeah, so 8 comma 0 and 0 comma 8. So let us assume my 8 comma 0 is here and my 0 comma 8 is here. So I get something like this. 8 comma 0 is that vertical line, 0 comma 8 is somewhere here, so I get this. I get this as the last one. Okay. This is my last one. Now this is a target that I have given. Now I want to minimize rho 5. Now this is a direction of increasing rho. This is rho equal to 0. So every point here has rho equal to 0, but I am not getting any feasible point. So I now have to increase this rho in order to get a feasible point. So this will force me to get a feasible point by increasing this rho 5, which means you move this line parallel to itself upwards till you touch this 10, right? You are at 8 here, so you need to move this a little upward till you touch this 10. So you will finally get rho 5 is equal to 2, and the point that you will touch will be x1 equal to 0, x2 equal to 10. That is the point that you will touch. So what will happen to your problem is the solution to the goal programming problem will be 0, 0, 0, 2 given by this. It will also give you, these two are satisfied, this will also be satisfied because you are at 0, which means you have got that 800 satisfied. This is the only one that will be violated. So instead of setting a minimum target of 8 for this, you will end up setting up a minimum target of 10 for it. So this is the goal programming solution to this problem. We look at the goal programming solution to the next example in the next class.